This was originally developed in VisualWorks, but it's also usable in Object Studio, and I wanted to underscore that point. Andreas is going to show us a demonstration of it running in Object Studio, and he uses it in the last 5 minutes. So multi-core computers is it's almost impossible now to buy a computer that doesn't have multi-cores. So they're ubiquitous. Quad cores will have 8 cores, 16 cores around the corner. So we want to try to see how we can take advantage of it. So this started out as they were starting to become more and more prevalent, and it was obvious that they were going to take over. I made an item on the small talk roadmap that we have. Research ways to leverage multi-core computers, and it got a lot of interest. So what's the attraction? You really want to make the most of what you have. And so this is a quad-core computer, and when I run an image and do some heavy number crunching, one of these basically maxes out, and it tells me you're using 25% of your computer. 25%? Well, that says there's just a whole lot more waiting for you to take advantage of. What I really wanted was Mike's computer that he demonstrated this morning. I had a whole lot more of these. I like that. So if our IT guy can order one of those for us, that would be great. More of this kind of stuff. Just a little bit about performance. So we're trying to get more performance. What are some ways to get performance? Well, there's a couple of things you probably want to explore first before moving to something like polycephaly. The biggest bang for the buck you're going to get is if you change your algorithms around. And Smalltalk is really good for that because it lets you see the forest through the trees. You're not down at such a low-level implementation detail. You can still rearrange things and use different algorithms at a very high level. And it's those kind of changes that give you, 2x, 5x, 10x improvements. After you kind of find something very useful there where you've gotten some good improvements, the next thing is to go through the profiler and find where the time is going and find better ways to do things. You're not going to get a 5 or 10x improvement out of those usually. More realistically, you might get 10 to 20% by finding where some of the bottlenecks are and finding slightly better ways to do that. Now, polycephaly is not another area where you can start to get some real benefits. Back up. Grace Murray Hopper, I was really happy to see yesterday in John McIntosh's talk. He mentioned this because a lot of times I bring up Grace Hopper and a lot of people don't realize who she is. So I had it was funny, on the way out here, the plane right out here, I grabbed a magazine that just came in the mail, Maximum PC, and I opened it up, the first couple pages on the plane ride out, and it says the 6 most important women in computer history. And of course it mentions her. And she is famous for a few things. One of the developers of COBOL, of course, getting the moth out of the relays and said we're getting the bugs out of the system. So bugs. I had the privilege, though, some years ago, of being in one of her presentations. And she had a real knack for making some difficult things really, really simple and intuitive to understand. And I always remember one of the things she said that if a farmer is pulling a stump out with a horse and he can't get the stump out, he doesn't go back for a bigger horse. He goes back to the barn for another horse or a team of horses. So that's really what a multi-core computer is like. It's a team of horses. And of course, we can do a type of concurrent programming. There's a couple other things that you might be able to do since it's one processor. You've got one operating system. You may have some other options, shared memory, because it's all on one box. But one of the biggest things, concurrency is generally not easy. It's non-trivial. I mean, this problem doing concurrency, it's been studied for decades. There's lots of research. There's lots of ways to do things concurrently. But none of it's really trivial. I mean, there's some okay to good ways, and there's lots of bad ways. Even if you do some really simple problems, some really simple producer-consumer problems, if you've ever had to debug or ran into a problem with one of those, also just even a very simple problem, you can get some very difficult to solve problems or bugs that have you scratching your head trying to figure out what's going on. To kind of underscore that point, both AMD and Intel, who are putting out a lot of these multi-core processors, are donating people and money to universities to study concurrency, to get better ways of doing concurrency. So it's a recognized issue. One of my favorite quotes, as the power of using concurrency goes up linearly, the complexity goes up exponentially. So when you start leveraging concurrency, and you start, if you have any kind of complexity thrown in, it can really make things difficult. One of the things I like about, well, actually, I'll do that later. So what I'm going to talk now is some different approaches that could be taken to leverage multi-cores. The first one would be to have multiple applications, and this one is obviously the simplest. Next slide. The advantage is it's simple, easy, it's effective. The operating system takes care of all that. If you're running many applications on a multi-core computer, it just uses the multi-cores. Disadvantages might be that you need independent applications, and you're not necessarily using those applications for trying to solve one problem or set of problems. Another approach, multiple process threads in a single application. Next slide, please. The advantages of this is the threads can have access to the same object space, so you can use them to help solve a single problem. And it can be very effective. And there's a lot of this out there. Disadvantages might be that, okay, now you have to manage contention and sharing of all your objects. So there's some overhead you're going to have almost no matter what. You do add complexity. We've had before, it's done, if one thread goes down, it is possible to bring everything down, so some possible disadvantages. In VisualWorks and Object Studio, when you fork a block, you get essentially a green thread. It's not a native thread, but it's a nice, lightweight, fast process. It's not mapped to a native process, so it's not true concurrency. But there is a place for these, and where they're useful, they can even be better than having native processes. And I'll talk a little bit about that. They can be really effective for coordinating concurrent work. So I'll show you an example of that later. Next slide. Some objects we have in Syncom Smalltalk for managing concurrency. Processes, I mentioned, which are green threads. Semaphores, promise, which is a type of future. And shared queue, which is a type of collection that manages adding in and removing objects from a collection from multiple processes. Manages doing that safely. Another possible approach would be to have multiple threads in a virtual machine. So imagine if you had one thread doing execution, one thread doing your JIT, another thread doing your garbage collection. That might be a way to have even a single-threaded application, but you're using multiple native threads. Advantages would be that you could use multiple cores within a single-threaded application. Disadvantage would be probably a lot of work, a lot of time, a lot of resources to build a VM to do that. You'd have to do some research to see, well, is the end result even going to be worth it? So expensive, but it's a potential option. Another approach, and the approach that polycephaly takes, is coordinating multiple applications. So what polycephaly, you'll see, what it essentially helps you do is manage starting up additional headless images, giving them work, and getting the results. So the advantage of that is it's fairly simple changes in code to take advantage of this. It's simple and effective. You can scale to any number of cores that you've got. And we'll talk about it. You can even go, there's a rough rule of thumb, you want to go like 1.5 times the number of cores that you have for maximum throughput. There's not too much contention, maybe some of the hard disk if all the images are isolated at once. And we can do it without any VM changes. So it was simple, effective. Disadvantages, you need independent pieces. This is not something that you can use for every single problem in trying to gain concurrency. So it's effective for a subset of problems, but for this subset where it's useful, it can be really useful. Another variation that's possible is that you have the same kind of thing, but shared memory. Next slide. And that might be applicable to a broader set of problems since they can access the same object space concurrently. But it kind of goes back to having the native threads. Now you've got to manage all the access to those objects and adding a lot of complexity. Also, you've got to think about now with multiple people accessing the same set of objects, that brings up a whole set of issues now for garbage collection. So again, it's a possible solution, but we'll probably take a good bit of work to make this happen. Next slide. So one of the things that I wanted with how concurrency was that it was often, when you had any kind of complexity in it, it made things pretty difficult. One of the biggest advantages I think that Smalltalk has is because it's such a it's so simple and powerful, is that it leaves you plenty of mental bandwidth for dealing with solving real problems, solving your business problems, solving your scientific problems. Well, Smalltalk is also pretty good for doing concurrency because since it's so simple, you've got lots of bandwidth for attacking those concurrency problems. But I don't want to waste all that bandwidth, trying to figure out and manage and work with concurrency. I want that to be simple too, so you still have plenty of bandwidth to solve your business problems. So what I really wanted was something Smalltalk simple. I would say KISS, keep it simple, Smalltalk. And basically with Pareto's law, I wanted 20% of concurrency things that would give me 80% of the value. I wanted the most bang for the buck, the most Smalltalk-like solution. So basically, I put something into our roadmap, basically challenging engineering. I said, this is what we want. And any takers? And luckily, we did have some takers, and some of the guys in engineering had thought about this problem and put what I think is a really nice solution to talk about. So what Polycephaly does is it assists you. It makes it really simple and easy to start up headless images, give them work, and get back the results. And I'll show you some examples and what we found in those examples. So at one point, this isn't saying, oh, we've invented something new. We've solved all the issues of concurrency. We have some magic panacea. That's not the case at all. We're just taking the 20% of concurrency things, and that gives us 80% of the value. We're trying to keep it simple. We're not giving you everything under the sun, just the things that are going to give you the most bang for the buck. So for what Polycephaly works for, it works pretty nicely. So I did some experiments. And my goal was, okay, take some code and now use Polycephaly and see what I can do with it. So, and basically 3 experiments. I apologize, this is a little bit hard to see, but this is some code. It says number queue. Basically, it creates a shared queue of numbers from 50,001 to 50,050. So I've got a collection of big numbers. And the work I'm doing is getting factorial for each of those numbers. That's why I'm using big numbers, because it takes more computation time. I want to see if I can bog down the CPU a little bit and see if we can do this with Polycephaly. So basically, process local just goes through, says is the number 2 empty? While false, generate result, which does the factorial. Generate result and factorial. So basically, we're just going to go through and get factorial for each of those numbers. And I'm going to do that locally and also do it remotely. Next slide, please. Okay, so here's process remote, and creating a semaphore new, putting the results in a shared queue because we're going to have multiple processes accessing them. Okay, here's Polycephaly. Polycephaly.virtual machines new 4. That's it. That creates and fires up 4 headless images that I can now give work. What I'm doing here now is going through each machine and forking off a process for each machine. And what that machine does, it says to the number queue, Give me the next thing off the queue, give it to the machine. When the machine comes back with the result, give me the next thing off the queue and give it to the machine, and then get the result back. And we keep doing that until it's nil, and we're done. And when that process is done, when there's no more things, so basically you have a queue of work. So you can do this lots of different ways. You can put work on that queue, and this basically gives it out to the machines. When the machine comes back with the result, it just grabs the next piece of work and goes to work. And then when that process is done, it says machine release. That shuts down the image. And then we signal the semaphore. And the reason we do that, because then we come down and say time to be done, wait. And basically what this will do is it will wait here until all of the machines have checked in that they've completed their work. So that starts up, does the work, shuts down all the images, and then returns the results. So how did that work out? Well, I had another process queue of very small numbers, so not much work. And running that locally, these results are in milliseconds. So that's 0.4 milliseconds. We need 0.4 seconds to do it locally, and 0.7 seconds to do it remotely. Well, it's not really even worth doing remotely because it's such a small amount of time. So that shows that there's just a little bit, actually not very much, but just a little bit of overhead for polycephaly in doing this here.
Pardon? Can I just...
Sure.
Does that time include firing up the polycephaly images?
Yes.
That's pretty impressive.
I was surprised. If your images are small, they're like lightning. When you start loading tons of stuff into them, you'll notice they do take a little longer. So, okay, so let's do it with the numbers that I showed you, 50,001 to 50,050. So doing it local took 308 seconds, and doing it remotely took 72 seconds, so less than a quarter of the time using polycephaly. This is a very simple example. So it's like, yeah, big improvement in time. That was relatively easy to do. Okay, experiment, my second experiment. Okay, load the daily data for all the stocks in the S&P 100. And there's 100 stocks in the S&P 100. And it would load the open, high, low, close, and volume numbers for every day since 1990. It gets them from Yahoo historical data. So it's doing HTTP calls, getting back, parsing all the data, creating a result. So that would take a while doing. I'll go to the next page, please. So loading those all up would take 84 seconds to do that locally. So splitting up the problem, if I fired up 3 VMs, that dropped it down to 21 seconds. So again, significant improvement just by handing the work out to a few other images, starting them up, giving them the work, shutting them down, cleaned everything up, and a big boost in time. So a big boost in throughput. What about other things? I know one of the things I originally did, and the question was asked, does this include starting up the images? And I remember one of the developing engineers of polycephaly was upset with me that I was including the image startup time and the shutdown time in these numbers. So I said I wanted to be very conservative. But for some of these, I said, okay, well, let's have hot VMs. I'm not going to include the time they're already out there, they're waiting, which might be a more realistic scenario for a lot of people using something like this. So I fired 5 hot VMs, and I brought it down another few seconds. And I said, okay, well, maybe more is better. Let's throw 10 hot VMs at it. And we got that. It wasn't really much, actually, it took a little more time. But the one thing to note there was, it's not a lot more time. It wasn't like this went up to 30 seconds or something like that. Yeah.
Any insight on why 3 VMs would be 4 times faster?
Yeah. Actually, I was wondering how some of it, using a 4-core machine I got, it was faster than a quarter of the time. The only thing I surmised on that was also maybe I had like a GC or something on the one local image, so there was a little more overhead, where you never got to that point with the smaller remote images that started up, did the work, and shut down. They didn't have to simply go through a GC cycle. But Mark?
I was just curious how many cores were involved in the results.
The machine I was running on here, my home machine, is a quad-core machine. But back up one step. The nice thing here was that even firing up all those extra unnecessary VMs didn't kill me on time. So I was pretty happy that that was efficient. So there's no, if I misjudge the numbers, at least not going to kill me. Okay, my third experiment was in loading thousands and thousands of market security information, not the data, but what about when stock exchanges went out. So loading everything from New York Stock Exchange, MatriX, NASDAQ, around 24,000 mutual funds, just the name, ticker, description, definition, and ETS, 584 of those. So here's what the code looks like: security, load New York Stock Exchange, load Amex, load NASDAQ. So one at a time, I've got five nice pieces of work here, which is really ideal for using polycephaly. So here's how long it took. That was, I think it was around 115 seconds. So it takes a sufficient amount of time. So now what happens when we basically make all five of those independent things and hand them out to their own virtual machine? So first of all, how am I going to do that? So I wrote a little bit of code. I basically got a promise where I passed in each piece of work. And once I have that promise, the way a promise works is you ask the promise for its value. If it has it, it gives it to you. If it's still computing it, basically you go to sleep until it's done, and then it wakes up and gives it to you. So what that actually looks like, I can put that on the next slide. Here's the promise. I said, okay, create a virtual machine, and you tell the machine to do the string. There's actually two ways to tell it to work. You can give it a string, or you can give it a clean block. And you can pass in values with that block also. The block is probably a little nicer, but the string is very simple and straightforward. So we get the value, so it sends it out to the machine, returns the value, then we release the machine, which shuts it down. And from this block, we create a promise. So that's all that does, so I can do that. So what happened? Well, we brought the time down from 115 to 80 seconds. Well, okay, it's an improvement, but it didn't bowl me over, and I want to be bowled over. I want a bigger improvement. So what do? You say, okay, let's dig in a little deeper, see what's going on. And when you check the time for each of those five things, here's what I found. Basically, they were all going in 35 seconds or less, except for one, which was taking me 80 seconds. So this guy loading the funds, there's a lot of them, that was the bottleneck. So let's take a look at that. One more slide. Okay, so that load of funds took the majority of the time. It was loading over 24,000 mutual fund definitions. It gets them via HTTP. The way I'd set up the way it was on the internet site to get them, I could get all the information for funds starting with A, and then make a call to get all the ones starting with B, all the ones with C, etc. So okay, well, I can make each one of those an independent task. Let's try that. So I started N drones, and each drone grabs a letter and says, okay, I've got A, let's get all the mutual funds, let's start with A, and we'll load and process those. Then it comes back and gets the next letter, etc. So, well, how many drones? What's ideal? Well, we've got a computer, let's try them all. So I tried running it from having 3 drones, 3 virtual machines, to 20. And here's the results for each one of those in milliseconds. And the sweet spot seemed to be having 8 right here. So you can do things like that to see, okay, well, what's the ideal? What's the ideal number to start up? And even if you misjudge it a little bit, a lot of them are relatively close. 3 we can do a lot better than 3. But once we got to 4 or 5, all the results were in the same ballpark. So some forgiving things about the number of drones you can choose. Points I wanted to make, of course, I talked about these include starting up the images and shutting them down. So, and also, of course, some overhead that you have is in transporting the objects from the remote images to the main image. So I think the ideal situation would be where you give it some work, it does lots of work and hands back a small result. If you're like loading up massive things and handing them back, it's going to be a little more overhead because you're marshalling and unmarshalling all those objects. So a lot of things to keep in mind as you're looking for playing with this to come up with the ideal solution. So let's take another look at the problem. Basically, I was making 26 HTTP calls, one for each letter in the alphabet. But you make the call, you sit and wait for the result, then you process the information, and then you do it for the next letter. So next slide, and here I kind of checked in, okay, where was the time going in that? Making the call was like no time at all. There was a huge amount of waiting time, waiting for the results to come back. And then processing it was pretty quick. So we've got all that waiting, so we're doing all of that waiting, then going and get the next one. So the load on the CPU was not too much. Okay, so the work is being done in sequence, where we're doing all that waiting. What if we could shrink, what if we could compress the wait time right out of there? And this is what it would look like if we didn't bring in the time a whole lot. And how can we do that? And the way we can do that is by forking off a thread. And these happen fast. If you want to, you can fork off 500 green threads just in a fraction of a second. So I mean, they are lightweight, they are fast, and they were an ideal solution for this. Actually, I don't know if you can fork off 500 native threads or what that might do. I'd be afraid of what it might do. But these lightweight green threads, you can bang off, and now we're basically compressing that time. As the results come in, wake up, and we do the processing. So I use 13 green threads and reduce the load time to 15 seconds. So it's from 80 seconds, squeezed way down. So we're doing a lot of wasted time there. And that was all in one image. That wasn't using polycephalon. So this was for something else worked even better. Next slide. But I can combine both of those and get the best of both worlds. So basically I had each virtual machine doing their own work, and then in the load funds, let's basically use the green thread solution instead of forking off more virtual machines. I didn't need to. So the end result was I brought it down from, I think it was 115 down to, what was it, 35 seconds? So down from 114 seconds down to 35 seconds. That includes all the image startup, transport time, and the cleanup of all of that. So there was quite a bit of an improvement in throughput. I was pleased with that number. Here's an example I had. I can send this to anybody who wants. Just basically a simple example of how to set up for, say you've got you're doing batch processing at night for all your customers. You have to do some processing, and you want to use polycephalon. So maybe you want to do all the customers whose last name begins with A and B as a means of breaking it up. So here's a simple commented piece of code for using and taking advantage of polycephalon. So just some observations. You want to measure the amount of time and dig in deeper to see where some of the time is going so you can best address the problem and improve things. Green threads were ideal here, especially for making lots of HTTP calls where a lot of the time is just sitting around waiting for the results to come back. You can do all those concurrently by using the green thread processes. So I ended up using both, which gave me the ideal, what I thought was the ideal solution. And keep it simple. Remember, as you start to get more and more complex, more and more difficult to track down bugs can occur. And the whole idea, I just want people to be able to take the code that they have and break things up with not much code change, just load polycephalon and go to town, boosting throughput on their multi-core machines. Other observations. The launch of drone images was not that expensive, especially if your image is small. They're very fast to scale up. The way polycephalon works now, the drone images that get started up are basically the saved copy of your main image. So one thing we get is people load polycephaly and try it and say, it's broke, it doesn't work. Save your image, because now polycephaly doesn't exist in that other image that it starts up until you've saved your image. So basically the nice thing about that is that all the code that you've got and you'll be calling is in those images. And we're looking at some possible changes in the future.
Yeah, I'm going to be removing that information.
There's also some other nice features. Say you lose your handles to those images, you didn't shut them down, or your image gets into a broken state. If you can shut down your main image, all the drone images go down also. So it does some really nice cleanup, doesn't leave you going through and shutting down all these things manually. If you start a local process which talks to a machine and you kill that process or terminate it, it automatically shuts it down. If you get an error on that remote image, the error notifications pass back so you can see what's going on. There's also a flag for those remote images. Say you've got a problem, you can start them up head full with a user interface so you can see the error and debug it right there. What's next for polycephaly? As Michael mentioned, one of the things, the ability to specify what image, I should say image, not VM. Integrating some things into base.im, possibly some pluggable marshalling. So I think most of the goals were made. One last thing before Andrea shows us demo, could you bring up that PDF? Yesterday afternoon, and this was perfect timing, one of our customers, Renard Jordahl, over in Europe, he sent me, he said, hey Arden, he says, I've been using polycephaly and I saw you were talking about it. Here's a little write-up I did, feel free to use it, which was very kind of him. Let's just scroll down to the second page. So, yeah, that's right there. So basically he talks about how they use it for testing. They build their product, they do a series of automated testing, which takes about an hour. So on a quad-core CPU, they got the time down to 28% of the original time. On this particular CPU, they got it down to 32. And on a dual-core machine, it came down to 43% of the original time. So I said, we're using it. Right now, polycephaly is in preview. I've been waiting to get feedback and things, but one of the really funny things, I've been trying to get the word out about this because I think this is a really beneficial framework that a lot of people can really benefit from in VisualWorks and Object Studio. So I really want to get that out. But as I've been talking to some people, they've been saying, oh yeah, we've been using that. Oh, it works great, fantastic. So I haven't really heard much feedback about it. People have just been using it. It works. And no complaints. People are happy. So I've been really glad to hear some of that feedback. Oh yeah, we're using that. We use it for our batch processing at night. You know, improve the throughput, 3x, things like that. So, last thing I want to do, Andreas is going to give you a demonstration and tell you a little bit about how he uses it for unit testing in Object Studio.
All right, thank you, Gordon. Independent of this company, here knowledge, I was using Object Studio, or we run a build pretty much every night for Object Studio. That build is automated and it runs a whole bunch of execute tests every night, and the next day we get an email with all the results, what has gone wrong or what happened. What we did was actually, all of a sudden we found out that the night apparently doesn't have enough time to run all the tests that we've got, and so we need something to speed it up. And polycephaly came along and there was like, oh wow, that we can use. So eat your own dog food and make sure that all of this stuff runs. So we had a small change to our test runner. And as Arden already showed you, run all tests. This is the code that basically is the same thing that ARM does. So what I do is just tell, I spawn a bunch of new virtual machines and tell those virtual machines what classes, what test suites do they have to perform. And then the tests are performed right now in eight different images, and then they're coming back for more. Return the result and come back for more. And what I wanted to show you here is that actually you can see that actually very nicely. I have the Object Studio. You see that there's the Object Studio executable right here. And I do a run all tests. And we want to inspect the results. And you see that we are opening up all those Object Studio executables. We do a whole bunch of tests with net shell and connectivity and all kinds of stuff. And then you should see in a couple of seconds that we actually release those machines. And boom, and they're gone.
How many CPUs does the machine have?
CPUs, 1. Cores, 2.
2 cores.
2 cores, yes. So what we do is basically just return the strings here and see that this is passed, this is here, one thing failed, and on and on and on. So we parse the thing, and the next day we know what has passed, what has failed in those tests, and we don't have to wait actually for another couple of hours after your working day has started to get all this stuff done. The only thing is you cannot rely on the order of events. Yeah, with everything asynchronously done, sometimes you don't get the order of events. Right now we sort it basically by class name, and every image gets a different class name. Of course, the suites, the test suites, are executed at a different speed. They're dependent on external resources or so, which means that they return in their own time. And if another thread or if another virtual machine has executed 2 or 3 different test suites in the meantime, of course, in the result they come before them. So if you have to rely on a certain order of events, you actually have to do a little more here and maybe put it together in a unit of work. What we've done with test resources, like with databases or so on, where you have a unit of work for databases for each test database, like Oracle or DB2 or so, because we only use one test instance, and if you have multiple images, deleting the database schema, creating the database schema at the same time, you run into a whole lot of trouble. So we created a unit of work here where we raise the database, run those database examples right there, delete the database, and then return the result. But we can run Oracle DB2, SQL Server, Postgres, SQL, all at the same time. Plus all of those images that all of those tests that I've run here before, icons and so forth. I tried, rather than the string that I've returned right now, I tried to return the whole test result, which would work with the exception that we have a couple of user interface results. And if they fail, in the SQL test, the result attaches or has a link to the original object, which means you're trying to marshal a user interface that is on a different machine, or not on a different machine, but is on a different image, and you try to get it back, which doesn't work. So right now we just pass images or strings back and forth, which works fine. Any other object works fine, except if you have a handle to something locally, like a database handle or a UI handle. That of course does not work. If you can transfer it from one image to another, then you're good. So that's pretty much what I wanted to show. Polycephaly basically runs out of the box. The only thing is what is it that you can do what's the smartest way to split up your work. In my case, I thought the smartest way was actually to do it by test tasks. Any questions? Yes.
Whether it was trying to launch the multiple images of Object Studio or VisualWorks, did you find, shall we say, internal resources, the resources that the development environment tends to rely on, not the SQL type of, or not the external database type applications, those types of internal resources that there was competition for, that there might have been problems with two images trying to compete for the same thing on disk at the same time or something?
No, the tests that we have are designed that you have a setup, you have a teardown, and the test is a logical unit of work that all of the tests for these resources are in this class. So that's by design in this case. Of course, if you rely on your test that your image is set up a certain way, you better make sure that the image that it finds those conditions. But right now, everything is contained in its own class, and it doesn't rely on external resources except the database tests.
So long as you aren't somehow modifying code to more than one image is trying to go to the changes file, you're okay.
You're not modifying code. I'm just the image is saved and starts up. So that's it.
All right, other questions? Okay, well, thank you very much.